Hello and welcome to another edition of Teradata TechBytes. My name is Tim Miller and I work in Teradata's Technology and Innovation Office. Today we're going to demonstrate two ways in which Teradata's Vantage platform supports the R language for data science and analytics. This is the fourth of a 5-part TechBytes series on this topic, which will provide you an overview of all the capabilities in Vantage for R and Python. My co-host for this series is Alexander Kolovos, an analytic architect in Teradata's product development organization. First, let's talk about the assumptions being made regarding the content of this TechByte, as well as the key takeaways we hope all listeners walk away with. There are two other parts of the TechByte series that should be viewed prior to this episode. The first is entitled Using R and Python with Teradata Vantage Release 1.1 Part 1 Overview, and the second is Using R and Python with Teradata Vantage Release 1.1 Part 2. The key takeaways from this TechByte include how to use the script and exec_r table operators to exec_r directly on Vantage systems, how to score models built outside of the Vantage ecosystem directly in Vantage, how to build multiple models simultaneously against a data partition directly in Vantage and save the models in the SQL engine of Vantage, and how to read those models and score them directly in Vantage. To review, this approach falls into user experience number 3, in which the language interpreters and corresponding R add-on package libraries are installed on each new SQL engine node. In this case, in-database analytics are provided via R scripts, invoked through SQL, and executed on every unit of parallelism. In this case, analytic task parallelization depends on data locale. This means there are two different kinds of use cases where this is an excellent approach. First are for row-based operations, in which data rows reside on a single unit of parallelism. An example of this is model scoring. Second are for partition-based operations, in which data partitions are on single units of parallelism. For example, simultaneously building many models for dimensions such as time, product, or location. These types of operations, row-based and partition-based operations, are sometimes called embarrassingly parallel. For global operations requiring access to all the data simultaneously, a MapReduce style of programming is required because, as you can see from the graphic, multiple results are received from every unit of parallelism, and the program needs to correctly aggregate or reduce them into a single result set. So what are the pros of this approach? First off, installing all the libraries and all functions are possible on this environment. You get out-of-the-box parallelization for scoring and scalar operations, and simultaneously model building against data partitions, and it provides an additional path to operationalization. On the negative side, the languages and libraries have to be installed on every node of the new SQL engine. Global operations require a MapReduce style programming. Debugging can be slightly more complex, and the end user must code in SQL. Next, let's talk about the two execution mechanisms that allow you to run R in Teradata Vantage nodes. The first is the script table operator. The script table operator pipelines the database I/O to R scripts executed in a batch Linux child process. Usage is secured and can be limited to executing scripting language of interest such as R and Python. To execute an R or Python script through the script table operator, there are several rules you have to follow. First, the user must install their script file on Vantage via an external stored procedure call. This registers the script to the system, making it kind of like a database object. Second, the user creates and executes a SQL query that calls the script table operator and invokes the script. And finally, the script executes in this Linux fork child process, which reads from standard in and writes to standard out, and runs on every unit of parallelism in this new SQL engine. We've already discussed the ramifications of this approach, which gives you out-of-the-box parallelization for row or partition-based operations, but requires a MapReduce style programming for global operations. Next, the R table operator provides in-database support specific to the R language. It runs in a protected mode within a secure server process on the new SQL engine, and it interacts with the new SQL engine through APIs in the same manner as normal user-defined functions do. To execute an R script using exec_r, a SQL statement is constructed with one or more on clauses specifying one or more input tables or objects, the R code for a contract, and an operator, which is passed to exec_r in using clauses. What is a contract? The contract defines a resulting schema. You can also optionally use a returns clause as is shown on the screen here. The operator itself is the actual R code that's going to be run in parallel. The R APIs are used to read and write data and read metadata just as you do in C++ or Java UDFs. And it has the same parallel processing considerations as script. One thing to note is that a barrier of adoption of these features has been installation and support to date. The great news is that in Vantage 1.1, Teradata will release a set of packages for both R and Python, which will be updated periodically and available for download on Teradata's Software Distribution Server, TSS. The package bundles will be in two parts: base packages and interpreters, as well as an excellent set of add-on packages for both R and Python. Everything will be installable via Teradata's parallel upgrade tool, and there will be CS change controls that will allow Teradata's customer service organization to get these things installed within your environment. And now let's get on to a demo. First, let's talk briefly about the use case for this demo. We're utilizing a use case in which models are going to be built to predict the propensity of a financial services customer base to open up a credit card account. We're going to do this on the population as a whole, as well as by state code. So first, various features are going to be generated by joining and aggregating from three base tables, customers, accounts, and transactions, into an analytic data set. This is basically what we showed in the second part of this TechBytes series. What's different is we're going to build a second data set to show how the Vantage table operators can be used to simultaneously build many models based on a partition key. In this case, our partition key is going to be a recoded state code variable. And we're going to use the top 6 states that this bank does business in an other state category. Then we're going to have two examples. In example 1, a model is going to be built external to Vantage, but then scored back in the Vantage environment. So for this example, we take a 25% sample from the first data set, and we build a random forest on an R client. We save this random forest model as an RDS file, and then we install it back on this Vantage SQL engine. A scoring script is installed and executed on the Vantage SQL engine using the STO to score the entire data set. In example 2, we simultaneously build many models based upon the state code. In this case, we're going to use the execr table operator with a partition by state code in our R script to build a model for each state code. Then we take a scoring script and we execute it by execr as well, reading the individually created random forest models that have been stored in the SQL engine to score the entire population. So let's start with example 1. Brought up to RStudio, and I've loaded my demonstration script. And the first thing we're going to do is we're going to load some of those packages. And notice I'm also loading tdplyr again because we're going to do some more wrangling in the second example. But I also load random forest because for right now, for the example number 1, we're actually going to build a random forest model on my client. Let's go ahead and load all those packages. We're going to establish a connection through ODBC and set the context. Once again, we see that the RStudio quadrant up here has connected the database, and I can scroll through databases and tables and columns if I'd want. Since we shared that before, we're just going to say, hey, I want to select a 25% sample from the same data set that we used in part 2 of this. Let's take a look at it. As you recall, you've got a customer identifier, some demographics such as income, age, years with bank, some indicator variables for gender, marital status, the state you live in, as well as your account indicators. And again, we're going to use CC account indicator as our dependent variable, and then some counts and amounts. You'll notice that the CC account indicator has come across as an integer. If I just pass that in to the R random forest function, it's going to try to build a regression tree as opposed to a classification tree. So the first thing I want to do is I want to go ahead and I want to set that variable as factor. That's going to tell random forest, hey, you're going to build a classification tree and not a regression tree. So let's go ahead and run the random forest algorithm. As in the case of calling the algorithm on the machine learning engine, we pass in a formula with the dependent variables and all my independent variables. We give it the training data set. We specify that 500 trees are to be built in total, and that at each level we're going to use 5 of those independent variables. Let's take a look at the model now. See, we got a really good error rate here, and you can see they give you a confusion matrix as well. The next step is to save this model onto my client. And I'm going to save it as an RDS file in this location here. Then the next step would be to execute this through a SQL statement. So I'm not going to be executing this code because what's going to happen is I'm going to create a new script from this file and then get this installed on the SQL engine. But remember, we're going to use the script table operator for example 1. So what I need to do is, I know I'm reading from standard in. I set a delimiter to a tab. I've set a file descriptor to standard in, and I build my data frame. Here's all of my data from my ADS_R file and all the data types. And the reason I have them listed there is I need to explicitly set them when I do the read table. So I create a vector of the column names as well as the column types. And then I do a read.table, passing it into the standard in, what my delimiter is, my column names, and my column types. And then I close standard in. Now, one of the things you have to be very careful of, since we're doing this on an MPP platform, is there are amps that might not have gotten any data. So in that case, you need to say, if an error occurred, let's set that input data frame to null, and let's get out of here and let the other amps that did get data work on this problem. The TDAT user is a special user for Teradata who executes all types of UDFs, including the script table operator. We've ensured that it has all the appropriate permissions. This is something your administrator has to do up front. I'm going to load some packages, in this case random forest, and I'm going to suppress the startup messages because I don't want to have stuff coming out. Again, this is running in batch on the Vantage SQL engine. The first thing I'm going to do is create a variable scored model in which I read this RDS file. And this is the location where it gets installed on the nodes, and you'll see that in a second when we go ahead and do that. Then I do the predict, and I'm passing in vote, so I'm going to basically get two different measures, a probability of 0 and a probability of 1. I set a new data frame, and I want to have within the data frame the customer ID. Predicted, there's actually two different variables for probability of 0 and probability of 1, and then I want the actual in there as well. And then finally, I do a write table out through standard out, and that puts the data back into the SQL engine of Vantage. So what I did is I copied and pasted into rfscore.r that code that we just reviewed. Next, I could go to any of my favorite SQL tools in order to execute these scripts that need to happen in order to execute this through script table operator. But what I'm going to do instead is I'm going to build a little BTEC script. So this is Teradata's tool to do batch SQL execution. So we're going to log in, and I realize I have my password there, and so all this, my friends in security, this is a demo. I wouldn't do this in production. I set my database to TDVDB. This is where I want my inputs and outputs. And then I'm going to set this special variable called search UIF DB path. So this is the database where I want my user install files, that's what UIF stands for, to be installed and where the system is going to read them from. So the first step is to remove the file if it exists, and I've run this before, so it does. Then we're going to install the file. So this is my scoring script that we just reviewed, and it picks it up from this location. But I also need to remove and install my actual RDS file, my model file. So I go ahead and do that. I dropped my table of scores first, and then I'm going to do a create table as and the select statement. So what I'm going to select is that customer ID, the prediction 0, prediction 1 that comes back from the call to predict, and then my actual, which is the CC account indicator. My on clause is I want to read all the data from my ADS_R, which is my input table. And then I have a batch script command in which I call R in batch, and I pass it the file tdvdb rfscore.r. I use a returns clause to specify everything that's coming back, and everything will come back in varchar format again. This is standard in to standard out. And I persist that table with a primary index on customer ID. So let's execute this. I'm going to write that BTEC file out, and then I'm just going to use the shell command. Again, I wouldn't do this normally. I would normally do this in a query tool, but for purposes of this demonstration, let's go ahead and do that. Excellent, that's done. So now let's take a look at what those scores look like. Just take a sample of 10 rows. So I'm going to do another db get query, and let's take a look at that. You can see top 10 rows or a random sample of 10 rows. I get my customer identifier. I get my probability of a 0 and a probability of a 1. In this case, they're extremely sure that it's an actual 1, etc. So this is the end of example 1. Let's move on now to example 2. So to begin example 2, we're going to do a little more wrangling because we're going to create a brand new data set that instead of state indicators, we're going to recode that state variable into 7 distinct values for California, New York, Texas, Illinois, Ohio, Arizona, and other. So how I do that is first create tables to customer, accounts, and transactions. And then when we build our customer data, as opposed to doing what we did with account indicators up here with the state code variable, I'm just going to say if it's CA, keep it CA. Otherwise, it's going to be an other. So we're just looking at California, New York, etc. I do the same exact thing I did in part 2 with accounts and transactions, and then we create ADSR2 this time. Different name, because it's a slightly different table. Let's go ahead and create that now in the SQL engine and take a look at it. Now you see instead of the indicator variables, we have California, other, Texas, California, etc. So let's split this up again, 60-40 split using the built-in sample function in the SQL engine, and call this ADS train test 2. Set a tibble to it, and then take a look at it. And now we have the sample ID again. 1 being the 60%, 2 being the 40%. We're going to make a filter for 1, and this time I need to persist it. I have to create this. Before we just created views when we were using tdplyr algorithms. So I'll go ahead and create a table that is made up of sample 1, and we have to persist these because sample is not deterministic. Okay, so that's enough of the wrangling. And now we're going to go over the code that we're going to pass to exec_r. So there's a special library called TDR. TDR contains the interfaces that you're going to have to call, which we're going to review here shortly, in order to read and write data and read metadata from the SQL Engine's data dictionary. Next, we're going to set the direction of a stream to read. We're only going to read one stream, so we're only going to have 0. And you remember the difference between script, or one of the key differences between script and exec_r, is that exec_r can handle more than one on clause, which would be a separate stream, and we'll show that when we actually score the models. My options are set to 0. I create a handle that calls our first TDR function, which is open. I pass it the reading direction and the stream in and options. I create 2 different data frames. One is going to hold all my data, and the other is going to read chunks of a data at a time. So I need to tell it what is that buffer size for each chunk, which I've initialized here, and I do my first read using another TDR interface called table read. That goes in DFN chunks. I want to check if there's any rows in that chunk of data, because this is the way I'm going to tell, as in the case before, did my amps get any data? This is especially important now because we're going to do a partition by eventually, and when we go ahead and build these models, and it's going to partition by those state codes. And so there's a very high chance that if you've got a lot of amps, that there's going to be a lot of amps that don't get any data. So it's important to check that row count, set your data frame to null, and then close that handle. If I did get data, then I want to continuously check my chunks, my n row of chunks, being greater than 0, and then continuously bind from that chunk back into my overall data frame DFN. Once I'm done reading, I close the handle, and now I'm going to call the random forest function. So again, I suppress the startup message, but I load library random forest. Again, because that came back as a non-factor variable, I want to set this as factor to force it into building a classification model. And I pass it in the formula, I pass it in my data, which is DFN, and the same exact parameters that I did before. Once that runs, then I want to write my data back out. So I set my write direction, I set the stream number, since my other stream's closed, it would be stream 0, and I set handle out to be TDR open. Our models are going to be stored in blobs, so in order to save them correctly, we need to serialize the objects coming out. Now remember, each one of these scripts are going to write a single row. It's going to be a state code along with the model for that state code. So since they are lobs, we need to call two interfaces in TDR to make sure that they are set up correctly in the output stream, and that's lob call to loc and lob append. Then we want to set the attributes for the state code index. We write the data out and we close that handle. Now it's time to take this code and execute it through a SQL tool. This is dbeaver, a cool little query tool that I recently discovered. And let's go ahead and execute this SQL statement right here. Here's all of our R code that we just reviewed. It's actually passed within the SQL statement. How you set this up is I want to create a new table called RF state code model. So my models are actually going to be persisted in the database. And what that's going to consist of is my state code and then my RF model, which happens to be a blob. I'm going to select all my data, and I have to do a couple things here. First, I'm going to cast total income as float because it came over as a decimal with only one decimal place. We want to treat it as float, and we also have to translate the state code using something called Unicode to Latin because it came across as a Unicode string. We're going to partition by state code. So what this means is at runtime, Teradata is smart enough to partition all my data such that only a single amp has all the data for a single state. And I'm going to return the varchar OC1, which happens to be the state code, and then the blob, which happens to be the model as well. So that ran already, very fast. And let's take a look at what the results look like. dbeaver is not going to be able to tell you what the blob looks like. It's a binary object. However, you can see that for all my 7 state codes, I do have a table that's out there that contains a blob. Now let's talk about how we're going to score that. Let's go back to RStudio and take a look at the code to score these models. Again, we got to load the TDR library that has our interfaces in it. And all of this first part is going to be the same. I'm opening an input stream. I'm setting up 2 data frames, one for the chunks, one for the final data. I set a buffer size. I do a table read. I make sure that all amps have data. If they don't, we're going to get out of this script. I'm going to return. And then I read my data and close the input handle. The only thing different now is I'm going to open a second stream now. This is where I'm going to actually read my models. So I'm going to read those 7 rows that I have persistent in that table, 1 row per state with a model in it. So I set a variable myState to be the S code within my data frame, and then I'm going to read it. First read the state code, and if the state code is the one I want on this amp, then I'm going to read the lob. And I do that by doing a series of calls to lob open CL and lob read. I then have to unlist it and finally unserialize it back into my RF model. And since I'm only going to go through this once, I break at this point because I know I have the right state code, and I close my handle. Again, I'm going to load my random forest library in order to do the predict, and I call predict, again suppressing warnings, passing in my RF model as well as my input data that I read. I set up my scores in a data frame such that I have my customer ID, my state code, predicted again is going to be predicted 0 and a predicted 1, my actual, and I make sure that string as factors is false. Then finally I open up an output stream for write, I write my table scores, and I close that. Let's take a look at what that looks like in the query tool. Here I am back in the query tool. And you can see we set this select statement up, again passing the R code we just reviewed within the operator construct of the SQL statement. I'm going to select a customer identifier, the state code, probability 0 and a probability 1, as well as my actual value when I call exec_r. The select project list is exactly the same as before. On the first on clause, I'm going to partition by S code. And on the second on clause, I'm going to read my models. And I do that as a dimension. What I'm going to return is the customer identifier, the state code, the 2 probabilities, and then my actual value. So let's give this a run and see what happens. As you can see, this is incredibly fast. Everyone that's using exec_r, every one of our customers that's currently using exec_r is using it for this particular use case, I would assume, because it is so incredibly fast. Thank you for tuning in to part 4 of the TechBytes series using R and Python with Teradata Vantage. Have a great rest of your day.